I'm sharing my slides. Can everybody see it?
Yes.
Okay, good. So pleasure to be here. I was scheduled to go second, but then the order got switched because Professor Ghani had some emergency visit to hospital. So he told me to step in and do mine in his spot. Anyways, I'd like to talk to you about database dynamic modeling. And this is kind of my ambitious agenda for the lecture that will make a short overview of database dynamic modeling. And then two topics that I want to talk about: surrogate modeling and model using time series data. And time series modeling, you can start with linear time series models. Then there's a state space version of it. And then there's the non-linear version of it, which is recurrent neural networks. Now, let me just start off by saying that 1 hour is very limited time in terms of what I can cover as well as what you can digest. So I can either focus on a specific concept or method, very narrow the scope, in other words. I can go for a little more wider, broader scope and introduce many concepts and methods, but at much less detailed general level, so that my job would be to introduce that these things exist and what they are good for, so that you can go and study more later. And so I have chosen to do the latter as opposed to focusing on a specific method. So yeah, keep that in mind that I have a lot of materials. I will share my slides. I will send my slides to the organizer, which you can download and look. But I'm gonna skip a lot of details, and you can certainly look at the slides or go to the literature, or you can get back to me. All right, dynamic modeling of chemical process. So dynamic models are important, obviously, even though steady-state models are used quite a bit in plant design. Dynamic models are still important for assessing things like operability and controllability, design and testing of control systems, hazard safety, environmental studies, as well as while you're operating the plant, you may want to do online optimization or model-based control. You want to build online operated decision support tools, validation of operating and safety procedures, and you may also have simulation-based operator training. Okay, so the idea is that you create this dynamic model, and you can simulate, you can analyze, you can optimize, you can do various things with it. Now, what you may receive from the process itself would be measurements, data, right? And you can incorporate these measurements to assist the model, certainly, because there may be unknowns in the model. You may want to estimate parameters, you may want to estimate disturbances that happen, and so on. And then using the model, you can suggest improvements in terms of design or in terms of actual operation, adjustments in the operating condition. Okay, now in terms of dynamic models, the model that we are familiar with, a first principles model, right? So we build models based on what we know about the process, kinetics, transport, thermodynamics. All those are put together in the form of mass-energy balance. And of course, there may be some parameters that you don't know and you may have to estimate from the data, but they require a relatively small amount of data. And of course, they are fundamentally correct that they can be extrapolated. Okay, they can handle nonlinear complex relations. They can be extrapolated. They have physical interpretation, but the bottleneck can be quite complex, involving thousands of or tens of thousands of variables and equations, and they can be very time-consuming to build for industrial processes. Okay. On the other hand, the more practical solution maybe to use data to build models. That's what we're going to cover here today. And compared to first principles, because you're starting out with nothing, that you will have to draw upon a lot of data, right? All the information that you have to come from the data. And the model will be as good as the data, basically. If data is not good, model will not be good. If data is concentrated in certain narrow range, that's where the model will be valid, but not outside, and so on. So extrapolation usually doesn't yield very good result. And basically, most database models are black box models, and there is very little physical interpretability that you can expect. But you can use it relatively easily on any systems that you have data with. But again, quantity and quality of data sets are important. So you got first principles model at one end, database model at the other end, and then you have so-called hybrid model. So you are trying to mix first principles with data and fill in the parts that you don't know, right? So as an example, for example, you are building a first principles model, but you know that there are things missing, or the phenomena that you haven't covered in your first principles model, and uncertainties and so on. So then you may want to use the data and kind of build in the residual. So you have a model for the residual essentially, which will supplement the prediction from the first principles. So that's an example of hybrid modeling, but there are many different forms of hybrid model. For example, you may not know kinetic expression, and you may want to leave that as a black box. Okay, so you leave that as a black box, and then you write down everything else in terms of mass energy balance, and then try to use the data to estimate that black box. That's an example of hybrid modeling as well. Now, I want to talk about surrogate modeling in particular. Now, what is a surrogate model, and why do you need it? First of all, suppose you have a rigorous model. You've done all the work in terms of getting the phenomena figured out and mathematically expressed and so on. But they may still be very difficult to use in practice because it's so complex, okay? And most engineering problems where you're trying to use model may require a lot of simulations and evaluation of the objective functions and constraints. For example, you are trying to optimize certain, inputs or design parameters, and every time you are iterating on the optimization, it may require evaluation of the model. And computational cost can be a bottleneck, even though computers are very good and so on. Numerical methods are good. They're still, they can be quite time-consuming. So direct optimization using a model that involves lots of equations, PDEs, and so on, may be impractical. Okay, some examples are shown here: multi-phase ion reactive systems. Here's, I think, pressure swing adsorption systems, and the CFD simulations. All those are very difficult to use in the context of optimization or control. So surrogate model, what that is a model of a model, essentially. Okay, so you have a complex rigorous model and you want to find a kind of a black box representation of it that is much simpler to compute. So what you do is you essentially have design parameters here, and you simulate your rigorous model to generate data, right? So you have certain inputs that you're trying to optimize over, and then you have outputs that you're interested. You are doing essentially simulation and creating data, and then you are training this surrogate model, database model, to represent this guy, so that hopefully this will be in much simpler form that you can use in more complex operations like optimization. Okay. So yeah, I mean, here's you have expensive simulation code, and using this over the design space that you have may be impractical, because every point that's indicated here, you may have to run the simulation, which may be too computationally costly. So you sample over this space, and then you create this surface meta model, so-called, and then you use this model instead to do the optimization. Now, what kind of surrogate models are there? The most common kind is this series expansion model. So you have basis functions, and you have essentially linear sum of these. Okay, and so your job is to determine what basis functions to use, how to generate sample, and then how to solve the optimization. Okay, so you have linear basis functions. I mean, this is just linear model. Polynomial response surface model. So you got zeroth order, first order, second order, so on and so on. Or radial basis, which is essentially a local model, right? That the function really depends on the distance. Okay, and there are different forms of radial basis. So these are what they call local basis functions. Polynomials are basically global basis, because they're not concentrated in any local point. Okay, and then once the basis functions are set, like here what's shown is the second order polynomial, right? Then your job is to create this estimation of these parameters. And that's relatively easy, right? Because these series expansion models are linear in parameter, right? Linear in parameters. So you can use least squares, the ordinary least squares, or some variations of it, okay? And to estimate the parameters. But you can also do other things. You can do like a support vector regression, where your job may be that you create this boundary, okay, and you're trying to penalize the deviation from this error bound. So everything inside would be considered, give you no penalty. You're only penalizing those points outside. So that's a different kind of regression. And the support vector machine, usually you don't use a linear form. You use what's called kernel function, right? Which represents a non-linear kind of basis functions. And then another popular model is so-called the Gaussian process, okay? And it's referred to it by different names, like the Kriging. People talk about Kriging, and that's essentially fitting model with Gaussian process. Okay, so the idea is that you got the Gaussian process here with some error, right? And this Gaussian process model specifies the mean and the covariance. Okay, so you have essentially n data points here with the mean and the covariance functions, right? And these are given by the Gaussian functions. Okay, and then you can just use the well-known conditional distribution expression to estimate, function value at another. So you have n data points, x1 through xn and y1 through yn, and then any in between points you can calculate based on this expression of conditional distribution. So what you're doing in kriging is you have n size data and you're essentially putting it into n-dimensional space. Okay, so the model, the model size, the basis function grows with the data size. Okay, so let me just, since we don't have a lot of time, you can look into this, but let me just pictorially express what's happening. Okay, so what you start out with is let's say that you have some unknown function, right? So the predicted mean function may be this blue dotted line, and then you may have a covariance, okay, which you start out with fairly something that's 2 sigma bound, okay? So you don't have, your prior may not indicate anything about the function. And then let's say you have samples like this, indicated by this red dot, okay? So now what you're doing is using this prior of the mean and the covariance. Now you're updating conditional distribution, okay? So your mean function, because now you have read these points here, your mean function has changed. Your mean function has changed to this blue here. So that's much closer to the real function now, because you have this point, this point, this point, this point, this point. So based on what you have gotten as data points and the prior distribution, the a posteriori distribution or conditional distribution gives you this updated mean as well as the covariance. So the unique thing about this kriging and conditional distribution is that basis function, number of basis functions are not set a priori. They keep growing as you add more and more points. Another unique thing about it is that you can actually get uncertainty in your model, right? So you have this blue as the model, but you also have this 2 sigma bounds, for example, or 3 sigma bounds, whatever you choose to work with, okay? So you can actually create bounds on what you estimate. And as you add more points, right, you get closer and closer to real, as well as these bounds will get smaller and smaller. That's the idea. And you can see that, you know, where you have the points, unless you had like a measurement error, and that was one of the hyperparameters, but you know, that your point is exactly your estimated mean value, right, at that point. And you have no uncertainty. So yeah, you know, we looked at series expansion model. We looked at the kriging model, and now the final model that people use quite a bit is this artificial neural network. So I'm sure all of you have seen this somewhere. Okay, that you got inputs layer, and they are forming weighted sum here and going into this activation functions, what's called hidden layer, to go through this nonlinearity. And so this weighted sum becomes an input to this nonlinear function, and it has output, and then they are added again in the next to form next layer, and so on and so on. Okay, and so that's the neural network. And they are trained. I mean, what's the feed parameter here in fitting the model? The feed parameters are these weights. So you know, as you go from one layer to next, the inputs form a weighted sum here to become the input to the next node, next layer's node, right? And how you weigh different inputs, okay, becomes your fitting parameter. And this, how you determine these parameters become important, and they are done through what's called backpropagation, where you look at the gradient. So that's pretty well known. And I'll come back to that later. Now, sampling is important also. Okay, when you form surrogate model, you create samples. How do you create samples? Well, you want to create samples where the operation range that you're interested in, the input range that you're interested in, would be well covered, essentially. Okay, if you have a wider space, higher dimensional space, you will need more samples in general, right? And you can do Monte Carlo sampling. I mean, that's very popular. That's a random sampling. And you may not get very good result unless you use a lot of samples, because these are samples that are randomly chosen. And depending on realization, in some realization you may get samples that are well spread out, but in other cases you may not. Okay, and so if you have relatively low number of samples that you're going to use, deterministic samplings are, or semi-deterministic samplings are more effective. And the popular method is Latin hypercube, where you're doing something like this. So you have this n by n grid, and you randomly chose this point. Now you're excluding this column and this row here, and then you are making another random choice among these white open grids. So now you chose this, and now you're eliminating this row and this column and so on, and you keep going essentially until you create n samples. So that's Latin hypercube, and that creates fairly well spread samples. Okay, and of course, once you create your surrogate model, you have to validate it, and the way you do it is usually you divide the data into training set and test set. And that's true for any database modeling, right? And so you use training set to fit the parameters, essentially, right? Fit the parameters. And then you use the test set to cross-validate. And you use things like the mean square cross-validation error and see whether that's reasonable. Okay? Let me not. I've already mentioned hybrid modeling. Let me just move on, since we don't have a lot of time. Let me show you an example here. So this is a CO2 capture process, right? So you have CO2 feed, and you're absorbing the CO2 with some sort of solvent, and then you are kind of stripping it to separate out the dissolved CO2, and then you are recycling the solvent, essentially. So that's, you got absorber and you got stripper, and then there's some sort of heat exchangers here for energy integration. And it's a very complex process because it involves ion reactive reactions, ion phase reactions, and it's multi-phase and so on. So yeah, I mean, the absorber, you got this kind of multi-phases, liquid phase, vapor phase, and inner phase, and then there's a profile. You have to consider reaction kinetics. And then stripper, you can assume equilibrium, and then create some sort of a linear profile. Anyways, the rigorous model is very complex and very difficult to use in the context of optimization, as well as economic evaluation, right? So what in our case, what we tried to do was we tried to put this capture process as a part of the reaction, the processing pathways going from CO2 source to some sort of product. And we create like superstructure network and try to come up with the best pathway using process synthesis. And putting in something this complex into that superstructure is just impossible, okay? Because you'll have to do a lot of evaluation for different options and just computationally too expensive. So what we tried to do was we tried to create a surrogate model where input will be things like the CO2 mole fraction inside flue gas, because you get different CO2 mole fraction of the flue gas depending on where the source is, right? You know, whether you have a natural gas plant or power plant or some sort of industrial flue gas, you know, they all have different CO2 concentrations. Amount of essentially the flow rate, okay, the amount of the CO2 gas, and then flue gas pressure. So pressure is input, and you know how much you want to capture is also input. So that's kind of like the operating condition. Okay, you may want to capture 80% of the incoming CO2 or 90% of CO2. And what I want to estimate is depend, you know, once these input conditions and my objective is specified, I want to know what the specific steam consumption rate will be, how much steam I have to use to accomplish this separation, as well as what the equipment purchase cost will be. Okay, and just imagine having to do this through the fundamental model that involves, I think, tens of thousands of equations, right? Just very, very difficult in the context of process synthesis. Okay, so what we did is we created this training set with different CO2 flow rates, CO2 mole fraction, feed pressure, CO2 capture. All these inputs were varied, right? So we create different conditions, different combinations, 13 different conditions, well, 22, but we used the next 14 through 22 as the test set, right? And in creating this data, what we had to do is we actually had to optimize the operating conditions of this capture process. So there was quite a bit of work to be done in terms of, because we wanted to minimize the amount of steam that was used. So we actually had to do the process optimization for the condition given so that minimum amount of steam needed would be calculated and so on, you know? And so all those optimization was done for different data points, and then the outputs were estimated, predicted steam consumption rate, as well as the equipment purchase cost. So each data point is generated by optimization of the capture process with respect to CO2 avoidance cost. And then the hybrid modeling, we have to, the surrogate modeling, we have to create this structure. It could be total black box, but in our case, we have given this nonlinear transformation. Okay, so we have given this form here, logarithm of the effective partial pressure, for example, logarithm of the feed flow rate, and so on and so on. So you can see the specific form, and this came from really our knowledge of the Clausius-Clapeyron equation, okay, which looked like this. So our model structure was inspired by these thermodynamic relationships of the heat of absorption. Okay, so we feed it this form of model. Our parameters were alpha, beta, gamma, and so on and so on. And the feeding was done. And really, the results were quite good. As you can see, what's shown here, data for feeding, the open dots, and black circles are the ones that are for validation. And you can see they are pretty much on the straight line, right? So very little error, less than 5% in terms of steam consumption rate as well as the capital cost. So the whole thing was done pretty well in terms of data generation, in terms of choosing model structure and parameter estimation. Here's another example, which can be found in the literature done by Farouk Hassan, and this has to do with I think, adsorption process, pressure swing adsorption process, right? And, adsorption processes are dynamic processes. They are cyclic processes. So therefore, they are expressed through this dynamic time partial differential equation, right? So you got spatial derivatives as well as time derivatives, and you have to discretize it, and putting all that discretized equation into optimization, it becomes a big mess. And so what they created surrogate model, but they did it in 2 steps. They wanted to get to eventually things like the economic performance, right? But they couldn't do that in 1 step. What they did was these nonlinear algebraic PDE models. They simulated it, and they created a surrogate model that relates input to output using kriging. So they used the kriging and Latin hypercube sampling, and they created this surrogate model. And then using this surrogate model, they could perform the optimization, because they couldn't do the process optimization directly on these nonlinear algebraic PDEs. So they created this surrogate model to do the optimization. And then once they optimized the process, they could get the data for things like the installation cost and operating cost. Okay. And then they feed it model of this form to create a function between things like the flow rate and the CO2 mole fraction to installation cost and operating cost. And then they did things like the using this simple economic equation, that they could actually use it to create CCS supply chain network. Okay, so you cannot use this original rigorous fundamental model to create this optimal supply chain network. That's impossible. It just takes too much computation, right? So surrogate model can be effectively used to represent something very complex like that at a higher level test, like the supply chain network design. Okay, I know I went very fast, and I warned you that I warned you about that at the beginning. So my job is that there are these things that exist, why you are doing surrogate modeling, and in what context they are used, as well as referring you to these references. So if you are interested, if you think that's something that you want to know more about, something that you could use, I suggest that you go to these references and study more. Now, what I want to talk about next for the remaining 25 minutes is models from time series data. Okay, so what's shown here are essentially, you got variables in this direction, and you got time in this direction, right? Okay, sometimes you have variables and runs and time, like batch and time and batch and so on. So you have higher dimension, but let's just say for simplicity, you got different number of variables, temperature, concentration, etc., and then you have different data at different time points. So that's time series. Now the thing is that you got these data are not independent because they are taken at consecutive times, right? So they will have what's called autocorrelation. They will have correlation across time, and they have cross correlation. So there will be correlation among the variables. Okay, so this correlation in time is called autocorrelation, and correlation among the variables across time as well is called cross correlation. So you got time-stamped sequence of variables. They are multivariate. Usually a very large number of variables are involved. You want to capture their correlation structure, right? Autocorrelation, cross-correlation, linear, and possibly nonlinear. And so that you can, once you capture this, what do? You can use these things like monitoring, fault detection and diagnosis, prediction, For example, you can do soft sensors or virtual analyzers. So maybe there are variables that you have very difficult time measuring online, and you want to use these correlations to predict these difficult to measure variables online using other measurements. And sometimes you can use it for optimization and control, but you have to be very careful when you want to use such a model for optimization and control, because you are creating certain patterns here. I mean, you are modeling patterns, given patterns. And when you optimize and control using the model, you may actually change patterns actively, okay? When you optimize, you may end up creating entirely different. So that's what you have to be careful. So it only works when you have inputs that can be independently excited, and you have plenty of independent excitation in the inputs. Then you can change it in any way you want to, and still the model will be correct. Okay, so let's take the very genetic kind of case, linear case, right? You got this kind of situation. So in linear time series model, you are trying to create this kind of thing. So you are trying to create trends in Y, let's say. And the way you do it is you have this so-called white noise sequence, so independent, identically distributed sequence. So this EK have no correlation, no autocorrelation, no cross correlation, right? And then you have this transfer function, dynamics essentially, which will create the correlation for you, autocorrelation, cross correlation. So this is what models the correlation essentially. So you are creating, correlation out of sequence that has no correlation, and that's your job, modeling H. Sometimes, though, in control and optimization, you have independent inputs, what we call manipulated inputs. So then we kind of treat this as separately, and we're trying to model cause and effect here, okay? Not just the trend, but cause and effect. So you got input U and output Y, and so what is the effect of input on the output? So that's a causal model, cause and effect model. As opposed to this part is pure trend model, okay? Caused by whatever. It could be caused by disturbance, it could be caused by something, noise, all sorts of other things. This is deterministic kind of relationship. You have a specific input that you are manipulating, and then you want to know what the effect of the output will be caused by that input. And then in time series models, you have different model structure. You may have heard of what's called ARCS model, right? ARCS model. So, or at least autoregressive model. You've heard of autoregressive model, right? So you got the essentially Y, which is expressed as a function of its own past values. But YK is a function of YK minus 1 to YK minus n. And then you got this independent noise sequence. Okay. Now, when you got this deterministic input, right, like a manipulated input, then they enter like this. So normally, without this U terms, it's called autoregressive model. But because you got this deterministic inputs in addition, you're trying to combine the trend model with causal model. That is called ARCS model. So X here stands for extra input, extra input. In terms of transfer function, it looks like this, right? So this is the trend model. This is the causal model, deterministic model. And our ARMA model, or our max model with this extra input, is that it looks exactly like this, except that now you got moving average of this input, noise input, E. So that's an RMAX model. And then there are other kinds of models, right? I'm not going to go through all these, but the most popular kinds are arcs and armies. Now, what I want to tell you is that it's fairly easy when you have when you are trying to model each output at a time, one output at a time. So let's say you got two y's. You can create a model for y1, and you can create independent model for y2. Okay, so you can create two models, one for each output. That's called the multi-input single output model or single output model. That's what people usually end up fitting. Why? Because when you start putting in multi-output model, okay, so now you say y1 is a function of not only y1 past y1s, but past y2s, okay, then it becomes a multi-output model. So this becomes a matrix now, okay, matrix. This becomes a vector and this becomes a matrix. It's very tricky. Why? Because you could end up with what's called the loss of identifiability. What that means is there may be infinite number of parameters that give you exactly the same thing. You have a singular estimation problem, essentially. Okay, and it can create all sorts of headache in parameter estimation. So instead, what you could do is you could actually create this state space model. Okay, so you got output, you got deterministic input, and you got noise term here. And essentially, you can kind of look at this as a combination of two models, right? X being having deterministic component and stochastic component. So this is like the H that we saw earlier, right? That's the trend. And this is the causal part, where you're expressing the effect of input on the output, deterministic effect. Okay, and they are put together into a single model like this. So that's a state space model. Now, the reason why when you have you go for this state space structure rather than this transfer function structure in the case of multiple outputs is because you have what's called subspace identification. So normally what you do is you estimate parameters using things like the least squares or pseudo linear regression. So what the very popular method is what's called prediction error method. That's a method that's developed by Leonard Leung. And so what you're doing is you're creating, if you have a model like this, and you're creating one step ahead predictor structure like this. So the idea is that I'm going to choose my parameter of my model so that this one step ahead prediction will have as little error as possible. So this is a one step ahead prediction error. This is a one step ahead predictor. If I had the model here, that is what I would use as the prediction. And so that's the prediction error. So I'm going to choose my theta. I have the data for y, right? So I'm going to use my data and determine theta so that this prediction error is minimized. And that's called the prediction error method. Okay, that works really well for transfer function models and single input, single output models. It doesn't work very well for state space models, obviously. So then people have developed this called subspace identification, which can be quite effective in identifying these multi-output models. Multi-output models are very important because if you identify model for different outputs independently, let's say I have y1 and y2, and I have a different model for that, then I haven't really captured the correlation between y1 and y2. What that means is that I cannot use y2 to estimate y1, which is what you would need for inferential type applications, soft sensors, for example. So really, you need multiple output model in order to capture correlation among different outputs to make the model really useful. Okay. So this, without going into detail, okay, that there's this method called subspace identification, which can just a non-iterative linear algebra operation, which will create a model like this. So from input-output data, the data for U and Y, you can create a model of this form. Okay, and of course, we don't have time to go through the details of it, but there's what's called M4 SID by Van Overshe and Moore, and Larry Moore, CBD. All these models are such models. So if you're interested, you can look at it. Now, as last part, I want to talk about recurrent neural network. So the idea of recurrent neural network is feed-forward network. It's just information flows in one direction, right? From input layer to output layer. That's the network, neural network that you're familiar with. Now, recurrent neural network, there's actually information that's flowing within itself. Okay, so there's what's called hidden state from the hidden layer, which will go back as input. So if you look at how the thing works, you got input layer that flows into hidden state and goes to the output layer, but this hidden state is carried over to the next hidden state. So therefore, your input at time one can affect output later on, because their information passed through all these hidden states. You see that? Okay, so really the idea is that through this hidden state, that X1 can not only affect Y1, but it can have affect Y2 and Y3 and so on and so on. And therefore, you will have way of expressing the dynamics within the data. Okay, and these activation functions that that people use are ReLU function or arctangent or sigmoid. Looks like this. And the way they are trained is so-called back propagation. Okay, so you start from the back and you have this loss function, right? So you want to minimize the data and what's predicted from this network. And then you have this loss function and you take the gradient with respect to these weights. And you keep propagating these gradients backwards. Okay, and that's why it's called back propagation, that you keep this error and you keep propagating backward for just these weights. Well, that's just showing how the recurrent neural network works for this large-scale power plant, and works pretty well. Now, what I want to talk about, which is important, is called the vanishing gradient. So this is a problem that exists in training this recurrent neural network. And it's not an uncommon problem. This is a problem that also exists for deep neural network, where you have a lot of hidden layers. So what happens is that as you calculate the gradient through chain rule, okay, that you keep multiplying these gradients. And if you look at like arctangent functions and so on, there's a very small region where the gradient is large. Otherwise, gradient vanishes pretty quickly as input gets larger, right? So for example, look at this function, sigmoid of tangent, right? Its gradient is pretty large here in the middle, but as you go towards the end, it quickly approaches 0. And so what happens with the vanishing gradient problem is that as you keep multiplying this gradient, okay, it becomes very, very small number. Okay, so as you may imagine, when you got this kind of many, many hidden layers, you end up multiplying these gradients many, 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 many times. And when you multiply number that's small many, many times, it just becomes essentially zero, right? And that way, what that means is whatever weight, you know, early on, whatever weight you adjust is going to have no difference at the output. At least that's what the gradient says. The gradient information says it doesn't matter how you adjust, it will have no effect on the output. So how can I train my weights here based on the loss function when the gradient says I have no effect on the output? So that's the vanishing gradient problem. Okay, that exists not only in deep neural network, but also recurrent neural network, because recurrent neural networks are like having many, many hidden layers. So then what happens is that people have found out that recurrent neural networks are not that effective for dynamics that last longer than 10 time steps. You know, very short dynamics, it seems to work pretty well. But anything beyond memory that lasts more than 10 time steps, it just didn't work. So that people have created some variations, like the long short-term memory. So what you have here is that you not only have hidden state passed on time, but you also have the so-called cell state. So, you know, you have something that's kind of recursively passed on, but you have something also inside that stays on much longer, in other words. Okay, so that's LSTM. LSTM is designed to overcome this vanishing gradient problem and the fact that RNN is not able to model really long-term memory. But it's much more complicated, obviously, to train. Okay, I'm going to skip the details because I know I only have 5 minutes before I have to pass the baton to Professor Ghani. But there's also another version, which is simpler. So this gate recurrent unit, okay, GRU, which is a simplified version of LSTM. So this works almost as well as LSTM, but has much fewer number of parameters. Structure is much simpler and has much fewer number of parameters, and is able to also retain long-term memory. Okay, so these are some of the things that you want to look into if you're interested. Recurrent neural network, something. If your application requires really long-term memory, then try LSTM. Or if LSTM is too complex for you, you may want to try GRU. And of course, you know, you need to go to the literature and study it, and so on. Okay, and then there's what's called attention-based LSTM. So what is attention? Attention-based came from, you know, this speech recognition problem where you have a long sentence and so it's difficult to translate long sentence. But you know, so the question is where to pay the attention, right? When you make the translation, which part should you pay attention to? And there's what they call context vector and so on, which enables them to look at right things at right time. Okay, let me just quickly show you an application we did with recurrent neural network, and to end my talk. So this is a loop-based oil plant, and so the idea is that, you know, it used to be that, you know, this heavy oil, right? Heavy oil from hydrocracker, they used to be useless, but now these heavy oils are actually very valuable material for creating loop order, right? So you can do hydrocracking, hydrotreating, and make it into very expensive, very valuable loop-based oil. And so the idea is to make this long story short, what they wanted to know is the kinematic viscosity at 100 degrees and distillation curves and so on. The problem was that they had online analyzer, but they had like a variable bias. Obviously, they had online analyzer and they have lab measurements, and they didn't match, and there was unpredictable bias. So what they ended up doing was they kind of looked at 3 to 7 data span, averaged the bias, and then ended up adding that bias. So this was a good problem for soft sensing or doing like an inferential analyzer, virtual analyzer, right? So what we wanted to do was we wanted to look at measurements of the process as well as the input, okay? And then using those measurements and correlate it to this kinematic viscosity and distillation curve and so on, okay? So we have the time series data-based inferential sensor for physical properties of distillates using the process variables. That's what we wanted to do. And then, once we were successful at that, then use these predicted inferenced property variables and try to optimize the processing condition so that this could be at the quality target that you wanted. And of course, applications like this, you have to do a lot of dirty work. Like you do data acquisition, a lot of data, 3,800,000 data, which came from 80 years of operation. And then you have to select right variables, right? Operation mode identification. There were different kinds of modes of operation. Simple pre-processing, okay, taking average and so on, simple outlier detection. And then we did the model-based outlier detection, missing value imputation, and so on, and filtering the noise out. And so a lot of work that went into cleaning up the data so that they are ready for modeling. And so the idea is that you have this kind of measurement that you get from input unconverted oil, as well as the VDU operating condition. So that's the process operating condition or process operating variables, as well as the past analyzer readings, right? And then you want to predict the future 1 hour plus kinematic viscosity. And same thing with the yield. And we use the recurrent neural net. And as you can see here, it looks pretty good, right? So the actual data is blue, green is the model, and orange is what they were using before. So using the virtual analyzer expressed in terms of this recurrent neural network, that you are able to improve the prediction of your kinematic viscosity dramatically. And they were quite very, the industry that sponsored this research was very, very happy with it. And the yield as well. Yield is, you can see that it's predicted. Model versus actual data. The trends are predicted quite excellent. So, models like this, all these recurrent neural networks or deep neural networks and so on, they are pretty good at modeling trends. And then there are other examples, which I'm not going to go through, but you can take a look. This has to do with LNG tanks and pressure prediction within LNG tanks. So I'm sorry that I had to go so fast, and try to cover so much material, but I hope that you've gotten the main point. I talked about the importance of database dynamic modeling. Then I went on to surrogate modeling. And when do you need surrogate models? Simulation models are too complex to run for iterative tasks like optimization. And so what does it involve? Well, you have to, first of all, create data set, and Latin hypercube sampling and running simulation. And sometimes you have to do process optimization as well in generating the data that you need. Then you have to select model structure. And we talked about different model structures, right? You could use some sort of a fundamental knowledge, like the Clausius-Clapeyron equation that I use for the capture process, or something black box like the kriging. And then you have to do parameter fitting. And then I went on to talk about time series modeling. And in time series modeling, what you're trying to do is you're trying to capture auto and cross correlation information that is in the time series data. And there are linear time series models, and the popular ones are like the ALX model or RMX model, output error model. But if you want to go with the multiple output time series models, where you try to capture correlation among different outputs, these models, ALX and RMX, may not work very well. And you may want to look at state space, subspace models. And then if you desire something that would capture nonlinearity, then you can, go for recurrent neural networks. But that's a leap in complexity. I want you to know that going from linear to nonlinear, now you have a lot of parameters and a lot of things that can go wrong, actually. Okay. And I talked about not only the vanilla recurrent neural networks, but there are things like the Lstm and GRU, which are meant to capture more long-term correlations. And it can be useful for dynamic monitoring, inferential sensors, etc., etc. If you want to use such a model for control and optimization, you have to be extremely careful. Why? Because data come with certain correlation structure, right? And the inputs that you're trying to use for control and optimization, the degrees of freedom, they better have certain excitation condition satisfied. They better be well perturbed. Otherwise, you are trying to use a model that has certain structure outside this structure. Okay, so when you use model for control and optimization, you could create entirely different correlation structure where your model will no longer be valid. Okay, so you are essentially using whatever model that you have built in wrong way. Okay, and for linear model, we understand this pretty well. We understand how to perturb inputs so that the model that you create will be pretty good for control and optimization. Something like the recurrent neural networks and all that, you're essentially flying blind. You have to be extremely careful. That's my point. Okay, so
okay, so Jay,
yeah.
Thank you very much for your very interesting talk. I see that there is a question on chat. Can you read it, or should I read it for you?
Isn't Lstm useless if you just use the ReLU activation function? I don't think so. I think Lstm really creates this long-term memory, and using ReLU activation function may help the problem, but it won't solve the problem. So.
Okay, are there other questions? So if I can ask one question from let's say, online control application.
Yeah.
What kind of model is most used?
Linear models.
Linear models.
Linear models. you know, what I showed you as you know, it used to be that people used the like step response models and impulse response models and sometimes ARCS models and things like that. But also nowadays, people use quite a bit of state space models. But I think using black box nonlinear models are extremely rare for control optimization applications. Simply because we don't know how to create a causal model of it.
But the linear model would be valid only for, let's say, small disturbances around the steady state.
That's true. That's true. But you know, you may create multiple linear models or something like that. That's what people do. They create multiple linear models and then they put them together to cover larger operating range. But you know, the thing about it is linear model, we understand how to create causal model.
Sure.
Correct causal model. Non-linear model, because the structure is so complex, we don't know how to even excite the input in such a way that the model is correct.
There is one more question there on chat.
There has been some recent work for utilizing RNN for RTO. What do you suggest? You know, I would say you're flying blind when you do that. So good luck. I mean, you know, if you really have well-excited input-excited data, you know, you are able to really shake the process pretty well, in the sense that you could perturb the inputs that you're trying to optimize. You may have a pretty good chance it may work, but even then, you know, dynamically, you don't know what's happening. Steady state, it may work. If you're doing steady state optimization, it may work. Yeah, that's another thing. You know, maybe when you say RTO, it may be just a steady state optimization, very slow steady state optimization. Yeah, that one I can see. If you have data where your inputs are well perturbed over the space that you want, it may work pretty well.
Okay, in the interest of time and not to keep other speakers waiting, I would end this presentation. Thank you very much, Jay.
Okay,
for giving this presentation.
Well, by the way, I will share the slides. So there are references there and so on. I know I went very fast, but you know, 1 hour.
Yes, if you can send us your PDF file of the presentation file, then we will upload it on our website.
Okay.
Okay, so thank you very much.
Sure thing.
So now we will start my lecture. My apologies that I couldn't start because I had to